G'day viewers. In this episode we are going to look at whether the Big Bang was a cold event or a hot event. Until 2001 this was an open question. However, the launch of the Wilkinson Microwave Anisotropy Probe, WMAP, difficult to pronounce, seemingly settled the question by measuring the cosmic microwave background radiation temperature. The fact that the cosmic microwave background radiation exists is in itself the evidence which confirms that the universe was much hotter in the past. So, as far as the standard model of cosmology is concerned, the Big Bang was a hot event and the discussion is closed. However, we challenge this perception. To be specific, we claim that the Big Bang was a cold event. In fact, we claim that the temperature at the instant of the Big Bang was exactly absolute zero, but rose to approximately 10 to the 31 Kelvin within 10 to the minus 42 seconds. This means that the hot Big Bang we perceive nowadays is hiding behind a cold Big Bang origin. In other words, the temperature of the universe rose from absolute zero to unimaginably hot so quickly that there is no way for our instrumentation to see past the hot Big Bang evidence in order to validate a cold Big Bang origin. So then, if we cannot physically validate a cold Big Bang origin, what can we do? Well, the only thing we can do is to appeal to common sense. What do we mean by this? Well, we're going to show you how we predicted the power spectrum Hubble constant many years in advance of experimental observation, utilising the same equation which predicts a cold Big Bang event. Therefore, it stands to reason that if our cosmic microwave background radiation temperature equation calculates the present day temperature value correctly, then it should also calculate the Big Bang temperature correctly as well. Okay, that's enough melodramatics from me. Let's get into it. Believe it or not, but the key equation we derived to describe the cosmic microwave background radiation temperature in the Hubble domain actually appears on the cover of Quinta Essentia Part 4. You'll see momentarily that it was first published in 2006, then distributed via retailers in 2007. The complete derivation of the equation shown can be found in accordance with the page numbers indicated on screen. Okay, let's learn a little bit more about the content of the book. In the Google Books About This Edition section, we assert the following. We utilise principles of mass energy distribution and similitude by zero-point field equilibria to derive the values of the present Hubble constant H0 and cosmic microwave background radiation temperature T0. It is demonstrated that a mathematical relationship exists between the Hubble constant and cosmic microwave background radiation temperature such that T0 is derived from H0. The values derived are approximately 67.1 kilometres per second per megaparsec and 2.7248 Kelvin respectively. What is important to note about this slide in the H0 data section is that we predicted the power spectrum Hubble constant in 2006, which was experimentally proven via the $900 million Planck satellite in 2013. This means that our 2006 prediction was confirmed approximately 7 years in advance of experimental confirmation. However, our prediction was not officially published into scientific literature via the Australian Institute of Physics until 2008. So, unofficially, we predicted the experimentally verified value of the power spectrum Hubble constant approximately 7 years in advance, and officially we did it in advance by approximately 5 years. Either way, the validation process is impressive. We beat a $900 million satellite. Moreover, as emphasised at the bottom of the slide appearing in purple text, the particle data group only recognised the power spectrum Hubble constant from 2013 to 2022. However, in 2023, the particle data group recognised the existence of the Hubble tension and officially published the power spectrum Hubble constant as well as the cosmic distance ladder Hubble constant. In addition, I will take a moment to point out that prior to 2013, the particle data group only ever considered and published the cosmic distance ladder Hubble constant. This is because the power spectrum Hubble constant was effectively unknown to science at the time because the appropriate experimental observations had not yet been executed. However, its existence was expected. What was unexpected was the eventual confirmation of the Hubble tension, that is, the apparently irreconcilable difference between the two forms of Hubble constant. Okay, let's talk a little more about our derivation of the cosmic microwave background radiation temperature estimate. In 2006, we estimated and published an improvement to the Particle Data Group 2006 value of cosmic microwave background radiation temperature. In 2008, our improved estimate was officially published in scientific literature via the Australian Institute of Physics. In 2011, the Particle Data Group published a revised value of cosmic microwave background radiation temperature in favourable agreement with our 2006 estimate. You can see from the information appearing on screen that our 2006 improved estimate stands as strongly in 2023 as it did in 2011. It has stood the test of time. It has survived for 17 years so far. Moreover, I will also mention that at the time of the creation of this video presentation, the Particle Data Group 2023 results appearing on screen are/were their latest published values. Okay, let's now look at our cosmic microwave background radiation temperature equation and understand what it teaches us about the Big Bang. In other words, we'll ask the question, was the Big Bang cold or hot? Before we answer the question about the Big Bang being cold or hot, we will briefly outline key features of the illustration appearing on screen. This illustration graphically communicates the primordial cosmic microwave background radiation temperature in the time domain. Please note that we have switched from the equation relating cosmic microwave background radiation temperature in the Hubble domain to an equation relating cosmic microwave background radiation temperature in the time domain. We are able to do this because at the instant of the Big Bang, cosmological spacetime was created, and the only possible relationship between the Hubble domain and the time domain appears as indicated. Thus, we have transformed the TU2 equation, which appears on slide 2, to the TU3 equation appearing on screen, inside the purple ellipse. The three important timestamps contained within the illustration appear as T alpha, T1 and T2. T alpha denotes the instant of the Big Bang. Please refer to the lower blue box. You can see that the temperature of the universe at the instant of the Big Bang was exactly 0 Kelvin. T1 denotes the instant of maximum cosmological temperature. Please refer to the upper blue box. You can see that the temperature of the universe was approximately 10 to the 31 Kelvin. Of critical importance here is to understand that the temperature of the universe rose from absolute zero to unimaginably hot in approximately 10 to the minus 42 seconds. So the Big Bang was in fact cold, but the evidence for this is hidden behind the hot Big Bang observations recorded by satellites. We will circle back to this and discuss it in greater detail on the summary slide. T2 denotes the instant of maximum post-Big Bang Hubble constant. Please refer to the magenta box. Let's now summarise what we have learned. Prior to 2001, the scientific debate about whether the Big Bang was cold or hot raged on. Then, on the 1st of July 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP. The satellite looked at the whole sky simultaneously and determined that the Big Bang was hot. Hence, the cold Big Bang dispute appeared to have been settled. However, our research demonstrates that the Big Bang was in fact cold, but evidence for this is hidden behind the hot Big Bang satellite observations we gather today. The universe transitioned from absolute zero temperature at the instant of the Big Bang to approximately 10 to the 31 Kelvin within 10 to the minus 42 seconds.